Okay, YouTube, in this my last video on sketching transformations of quadratic functions, what we're going to do is we're going to learn how to write a transformed quadratic function, but really start tying our transformations into this form here that we're going to be referring to as vertex form from now on. So I'll read through this with you. It says the lowest point on a parabola that opens up or the highest point on a parabola that opens down is referred to as the vertex of the parabola. So considering the fact that we've been really transforming this function f of x equals x squared, what we can see is that this lowest point that is on this graph that typically would start at the origin before it's been transformed. We'll go ahead and put that on here. Something like this here. We give that a name and we refer to that as the vertex of the parabola. The conclusions, though, that I want to draw tie directly into this vertex. Essentially, we're going to refer to this f of x. I'll write a little bit more cleanly down here. We say equals a times the quantity x minus h, quantity squared plus k. We have observed that this h value really is responsible for left and right shift, h units from the origin. We know that k is responsible for up and down shift, k units from the origin. We can see these kind of generalized here. But essentially, what we can say is this: the vertex form of a quadratic function is this form. We refer to it, though, as vertex form because the vertex is at the quantity hk, or the ordered pair, hk. The reason why this is true is because given the parent function starts at 0, 0, then anything translated away from this point is going to have the coordinates 0 plus or minus h, comma 0 plus or minus k. And so the values of h and k really directly always tell you where the vertex is going to be. It's going to be at hk. And in the event that we have just x squared, I want to point this out. We kind of have a as 1 times the quantity x minus 0 squared plus 0, where we have a k value, or an h value of 0 and a k value of 0. So using a, h, and k, we can actually really just directly graph these very, very quickly by determining h and k and saying that that's the vertex. And then this a value, what it's going to tell us essentially is if it's negative, it's going to be reflected over the x-axis. If it's positive, it's going to not reflect over the x-axis. In other words, it's going to open up or down. And it's also going to tell us about vertical stretch or shrink, given the fact that it's either going to be bigger than 1, in between 0 and 1, or equal to 1. So let's take a look at this example up here and talk about how we could use our knowledge of a, h, and k from now on to quickly graph and quickly write a rule for g, given g is some transformation of f of x. So it says, let the graph of g be a vertical shrink by a factor of a half. So we know that we've identified a vertical shrink by a factor of a half, and a reflection in the x-axis. So we have a reflection in the x-axis, followed by a translation 4 units up of the graph of f of x equals x squared. So we say translation 4 units up. The things that I instantly want to identify are the values of a, h, and k. Because if our intent is to write the equation of this, then we can really just say a times x, always minus there, x minus h squared plus k. And all we really need to do is go and fill in these values respectively for a, h, and k. So using what we know, we say, well, vertical shrink by a factor of a half. Vertical shrink says what it means and means what it says. So if I took it times a half, it's going to shrink by a half. So we know instantly that our a value is a half. And the fact that I say reflection in the x-axis, well, all that means to me is that this must be a negative value because we're opening downward. In terms of translations, well, we say 4 units up, and remember, up and down, k is responsible for that, okay, up and down translation. So we say 4 units up. K does not lie. It is indeed a 4. It did not say anything about horizontal translation, so technically the value of h in this instance will be 0. So to write this transformation, really all we need to write is negative 1/2 x minus 0 quantity squared plus 4. And just to let you know, yes, we can write g of x again, except for this time just write it thusly. We say negative 1/2 of our x squared plus 4. So we have up 4, opens downward, and vertically shrunk by a factor of a half, okay? So that being said, let's go ahead and sketch our function here. Since it was shifted up 4 from the origin, we're going to start up 4, use our translations here. And I know that this a value being negative means that it opens downward. Not only that, your traditional parent function goes up 1, right 1 to get to its next point. So since we're shrunken by a factor of a half, we would only go up a half and right 1. And the fact that this is negative, meaning it's opening downward, means that from this point we're going to go down a half, right 1. And because this has symmetry, we're also going to go down a half, left 1. And then very, very carefully we're going to sketch in our curve. Okay, so here's our curve. This is g of x. The last thing we intend to do in this video, though, is also state the domain and range. So the thing is, if you haven't picked up on this yet, parabolas always proceed from left and right for all of their domain, okay, for all real x values. In other words, you can plug in any x value, and it's going to cover some y value. It's going to pop out to some y. So because it goes left and right forever and ever, we say this is all real x values. All real x values, okay? All real numbers. And then the other thing we kind of want to denote here is this. Range. Range is talking about y values. Now I notice the highest y value that this ever gets up to is 4. This is 4. So we'd say the range of this really is all y values 4 or less on our y-axis. It'll cover those values. So we would literally say this. We would say that the range of this function is less than or equal to a positive 4.